say stuff. Dear Heavenly Father, we thank you for this morning and for the students. Just ask you to bless this class, Lord. In your name I pray. Amen. So I will, today is mostly show and tell. So I have a few things to show you, lots of things to tell you. To start with, these are all, in fact, things created by my, is it good? Oh, okay. These are all things created by my my brother Bill, to be more formal, William Cook of the University of, where is it? Appalachian State. I used to know it as ASU, but apparently ASU is something else, but whatever. Anyway, so basically the idea of this PDF is to explore the generalization of, everyone knows how to rationalize a fraction like that. We just multiply by what? 2 minus 3 root 5 over 2 minus 3 minus 2 over 3 minus 2 minus 3 root 5. And on the bottom, when you multiply 2 plus 3 root 5 times 2 minus 3 root 5, you get 4 plus 9 times 5, right, which is an integer. And if you remember, or if you've had number theory, you'll recognize that as the norm, right? That it's the norm that we can study properties of primes in, like, z adjoining the square root of 5, for example. And so we can actually create a norm of sorts, which is basically, if you're in some kind of extended object and thinking as a number theorist, a norm to you is just something that's integer valued, all right? So if we're working with, great. So the really all that you want to get from here is that the reciprocal, the way to do it is basically you just take 1 over a is equal to the product of all other conjugates of a except for a itself divided by norm of a. It's like norm of a has the product of a and all of its conjugates, right? Which, by the way, are Galois conjugates. So the conjugate of a with itself, that's the identity conjugate, which is kind of stupid, but any number is self-conjugate in that sense, because we always have the identity map in the Galois group. All right, so, yeah, we don't care. All right, so now here's where it gets fun. So let's compute the inverse of 2 plus 3 times the cube root of 2 plus the cube root of 2 squared, right? So you recognize this as being an element of q adjoin the what? Cube root of 2, right? Of course, the corresponding Galois extension is this guy, right? I mean, that's the splitting field for x cubed minus 2. We actually need these third roots of unity, right? Times the cube root of 2, which then gives us a solution to that. So he puts alpha equal to the cube root of 2. I might have called it theta at some point in here. I forget. And so now he's just creating stuff to work with. This is Maple, if you're wondering. You might notice something in Maple. There's a healthy use of semicolons and the output is in a different color than the input. The input is just one color, and it's clearly input. There's no syntactical meaning to white space in these expressions. It's a genuinely modern programming language. Just a comment. I don't know what other one I could possibly be talking about, but anyway. Yeah, it's not, of course, I'm not alluding to Mathematica. I would not be alluding to Mathematica. That would not be something I would do in here so underhandedly. Anyway, so moving on to, so there's your solutions to x cubed minus 2 I mean, it's still ugly. I'm sorry, but it's still ugly. But anyway, you get used to it, right? So he calls, I think he just basically creates names for the roots, alpha, omega squared alpha. Great. So the number we want to rationalize is a. A is equal to 2 plus 3 times that plus the, that. So this is that. And so Maple has built-in. Maple already knows everything I'm going to tell you, and it can do it with its, its core programming, or whatever you want to call that. What's the word? Yeah, it's a built-in function for Maple. rationalize that. It seems like a reasonable command. And so there it is. But the question is, how do you actually do this by hand? And that's what I'll show you. So just to make things a little bit easier to follow, Bill invents an x. He calls, let's see here, ax is really that. What is the x? X is just what is x in here? He says, let's call alpha x. So omega alpha y, omega squared alpha z. Our element A is that. Where's the y and the z? Is it? Oh, it's a times. Is it a times x? A times x. Oh. That makes sense because the last thing was what? Cube root of 2 squared. So what happens when you multiply that by cube root of 2? You can still see it here. So if you multiply that by the cube root of 2, this becomes 2. That becomes, that's weird. Yeah, this is not a times x, is it? He doesn't mean a times x. He means a in terms of x, doesn't he? It's 2, 3 times x plus, yeah. It's not a times, right. Sorry. Okay, and then here you go. Here's the Galois conjugates. A1 would just be, A itself, essentially. So x equal to alpha. Where I don't see where his y's are. I'm sorry. I substitute ax. Did ax have 3 inputs? There's something I'm missing here, guys. Oh, anyway. My point here is not to teach you Maple. So let me not be distracted. Okay, moving on. So however exactly I'm misunderstanding this code, not terribly important. The point is that this is the element that we're looking at, and these 1, 2, 3, 4, 5 are the non-trivial Galois conjugates. So, and how do you get those? You feed those. So we're looking at the Q, the splitting field being what? Q adjoin cube root of 2 and third root of unity times the cube root of 2. We worked out that the Galois group was S3, right? There's 6 automorphisms of that, and those 6 automorphisms either fix. What do? We could describe them. They either do what? They fix the. We look at in terms of cube. I can't remember how we did it. Rotate the cube roots, yeah. So rotate the cube roots and maybe just complex conjugation.
Oh, yeah.
Yeah, the complex conjugation usually gives you a transposition. The rotating of the cube roots essentially gives us a A3 inside S3. So if you have a 3 cycle and you have a transposition, you can generate S3 is what it boils down to. And so are you still using math in your daily life, Marissa? Some. Do you use lots of group theory? That makes me happy. Let's see here. You probably use more group theory than I do. It's very likely, even though I teach it. Okay, so anyway, here's your Galois. Here's the actual output. That's what we should be looking at. There's your conjugates in the sense of Galois of that number A, right? Here they are, right? And so if you multiply all of these together, if you look at it, right, you have every single, in this expression, you have basically the identity of something, sigma 1 of something, sigma 2 of something, sigma 3 of something, sigma 4 of something, sigma 5 of something, sigma 6 of something. If you take that and hit it with any automorphism in the Galois group, because sigma 1 through 6 just gets mapped to sigma 1 through 6 again, and they're permutations, right? That means that the norm, the product of A and all of its conjugates, has to be fixed. In other words, it's in the fixed subfield. So it's, yeah, it has to be rational. But in this case, it actually has to be an integer. Details. Well, there it is. It's 900. So but yeah, 900 is what you get if you multiply all 6 of these things together. And so 1 over A is simply the product of all the conjugates of A except A itself. So A inverse, and so I mean, you can't really, you have to see it. See, what this is simplifying the product of all the conjugates except for A itself divided by norm A, which is 900, and that's what you get, which is, by the way, the same thing that was spit out by the, built-in rationalization function for Maple. And check it out, it works. So he multiplied A by his A inverse, and so. All right, so there you go. He says this pretty much explains to you why we don't cover the conjugate cube root of 2 trick in high school algebra, as it is a little bit harder. It's a long way to go for this joke, but anyway. So I especially appreciated the effort Bill put into this, because it's, it makes a nice class of homework problems if you're careful to make it work out nicer than this. There are Galois problems to. You can look at rationalization tricks built from Galois theory using. This gives you, it kind of opens a different class of computational problems if you're interested for one thing. But anyway, any questions? Or? Okay. All right. So this next 2 PDFs, again, they're Bill's, I'd say they're Bill's fault. That's not quite honest. They're Bill's work. And in these 2 PDFs, the first one works towards, let me make sure I got them in the right, yeah. So the first one is on differential algebra. And the second one is on differential Galois theory. So differential Galois theory is built over differential algebra, right? Differential algebra is much like algebra you already know, except with a derivation. Okay, but you'll find the results I'm about to show you very, very familiar in some sense, and yet completely unfamiliar in another. So here it is. If we have a commutative ring with 1, you guys probably already know what a derivation is, right? It's linear, it means additive, and it obeys the Leibniz rule, right? That's right, yes, on the ring itself, not, not on functions of the ring. So a ring equipped with a particular derivative is called a differential ring, called delta. We'll call the partial the derivative, all right? And oftentimes we just use prime to denote the partial. If R is a differential ring and an integral domain, it's a differential integral domain. If R is a differential ring and a field, it's a differential field. Now he has some examples. Well, some general properties. First of all, the derivative of 1 is 0. And you notice that the derivative is a group homomorphism with respect to the abelian group structure of the ring. And so you get this, right? And so in fact, the derivative of any integer in the ring is 0. So, and furthermore, everything in the prime subring is constant, all right? So let's see here, prime subring. I don't know if we've talked about prime subring in your courses. We've talked about prime subfield, but this is prime subring. That I don't know. I think the prime subring might be the integers generated under the structure of the ring. Right. Or Zn, depending on the characteristic, right? Again, I don't know, because I'm not sure the definition of prime subring at the moment. Unless he defined it up here, I just missed it. Okay, but we're getting into the weeds here. Let's move on. So he also basically proves the sort of chain rule here of sorts, right? So if you have an element a squared, you get the Leibniz rule, but then that gives you 2aa prime. So essentially you have a chain rule built from these formal algebraic rules. And you can prove that by induction. If you have a unit, then you get this, which means you get that. And so he's, again, basically developing the power rule for negative powers if they make sense for you. And so in the context that B is a unit and A is anything, you get a quotient rule from these formal rules so far. So you're starting to see that essentially a differential ring is one in which you can formally do calculus, right? And you can say more, a differential integral domain. If R is a differential integral domain, then R's fields of fractions can be turned into a differential field in a unique way. And you can define the, this by the quotient rule, and it's going to be consistent with everything else that we've built definition-wise. All right. I mean, here he assumed that B was a unit. The point is, if you adjoin things being units, if they're subject to the quotient rule, that tells you how to differentiate them. The structure that you build is logical. So, like, again, the field of fractions makes sense as long as we define the derivative of fractions like that. We're already given a differential field, differential ring. Excuse me, differential integral domain, which means what? Commutative with the derivative. So that's pretty neat. Definition, a differential subring is a differential ring, all right, containing one, which is closed under differentiation. So if S subset of R is a differential subring, if one is in there, A and B is in there, implies the difference in the product, and also one extra. So this, up till here, it's like that's the subring test, right? But what's new? Just one extra wrinkle. You got to show that the subring is closed under differentiation for a differential subring. So you can talk about differential ideals, right? What's a differential ideal? A differential ideal is closed under differentiation. It's an ideal which is closed under differentiation, so it's still the usual definition for ideal in a real ring. And more than that, if you have a differential ideal, the quotient becomes a differential ring if we define the derivative on the cosets by the derivative of the coset. And a differential homomorphism between two differential rings is a map which is a ring homomorphism, and it must preserve differentiation, right? So phi of A prime is phi of A prime. There's a parenthesis that's misplaced here, I believe. That no? Oh, there's another parenthesis that I didn't appreciate. It's a syntactical parenthesis over here, yeah. That one is closed by that one. Yeah, I missed it. Thanks, Sam. So it's easy to show that the kernel of a differential homomorphism is a differential ideal, and the image is the differential subring of the codomain. And all the isomorphism theorems hold. Why didn't I make this a homework problem? These seem like awesome homework problems, don't they? Yeah.
Are there some rings of like the ring of real values functions that aren't different? Or like are examples of things?
What cannot be made into a differential subring? That I don't know. But he has a kind of stupid. He has the examples are coming. Some of them will be disturbing. So what's this lemma? I'm not going to prove anything. I'm just stating definitions and lemmas. I will not be dragged into proofs of things here. Otherwise, we will not get through. Okay, so I'm just telling you that at the start so that I won't be trapped into actually doing a proof in here of what we're covering at the moment, because I know I don't have time for that. Anyway, so if we have a differential ring and C is the kernel of the derivative, the differential subring of R, it is a differential subring, and it's called the constants of the ring. So the kernel of the derivative is the constants. Moreover, if R is a differential field, then C is a differential. So the constants form a differential field. In a stupid sense, because the derivative is 0 on them. So if you have the 0 map, it trivially satisfies all it's additive, it's Leibniz, you know? So here's a silly example. I think this answers your question, Sam. Any commutative ring with 1 is a differential ring when we just give it the 0 derivation. So rationals are a differential ring with 0 derivative, and by some of the above discussion, this is our only choice. Ooh, interesting. Because, you know, you can show that the 0 ring on the integers, the 0 derivative on the integers forms a differential integral domain of the integers. And then extend that to the field of fractions, which is the rationals. That's uniquely so. So this is the only way to realize Q as a differential ring field. Lemma, let F be a differential field of characteristic 0, and K over F an algebraic extension, like we've been talking about all semester. Then the derivation on F can be extended to a derivative on K in exactly one way. Okay, so if we have a tower of extensions, then if you got a derivative at the base of it, it uniquely defines up the tower. Well, at the end he has references. There's about 4 things he's using. This is one of them. But here's an example. The only derivation on the rationals is 0. Q adjoint square root of 5. We can figure out what the derivative of square root of 5 must be from its minimal polynomial, because that minus that is that. So if we differentiate that, well, 5 is a constant, right? So it differentiates to 0. But 2 times root 5 times root 5 prime has to be 0. Thus, this is that, which is 0. Yeah. But you can talk about more exciting things. You can talk about a logarithmic extension, or you can talk about an exponential extension, where the definition of logarithmic and exponential is both modeled on defining logs or exponentials by their differential equations. It's like an exponential is a solution of basically y prime equals to y, right? A log is what? It's a log. A log is a solution of what? What differential equation, how can you define a log? It says t prime is s over s prime. It's not immediately obvious to me why that's right. But anyway, here's the exponential expression. T prime is ts prime. I don't have a good intuition for quite the details here yet, but anyway, you can define exponential and logarithmic extensions. Oh, by the way, if you are just falling in love with what I'm telling you and you'd like to do this for your project in here, it's also possible. But you should actually do proofs, at least some. Right? Okay. Let's see here. Well, here he says, and it's also possible that I feel like I remember there's a typo in here, but I could be wrong. Well, for me, for some reason, I want s prime over s, but I don't know. I mean, I don't know, but I don't really entirely understand the mechanics of what's going on here. But he says that if this is the case, we could integrate. In other words, t is the integral of t prime, which is the natural log of s. Let's see, if we differentiate this, right, if the integral is the log, if we differentiate this, what do we get? We get t prime. T prime is, this is a typo. That's supposed to be s prime over s, right?
Yeah.
Because, like, this, if there's any justice, should be, if we differentiate log, it should be 1 over s prime.
Yeah.
I think it's just a simple typo here. Yeah, which may be transferred down to here. So I got to talk to Bill. I feel like we've already talked about this, and I forgot to make the corrections in his PDF, because we did this last year. Sorry. Okay, so likewise, this differential equation has solution. See, is that? Huh. Yeah, I don't quite understand this stuff in here just yet. I don't think it's that complicated, and I think there's maybe a typo clouding our vision too. Okay, but anyway, rest assured there's something called a logarithmic extension and an exponential extension, and these are pretty simply defined by something like that or that. In other words, we're adjoining an element T or we're adjoining an element S, which satisfies this kind of differential equation as it relates to the derivation, which is given. So definition, F differential field, constant C, a differential field extension, E over F is an elementary extension, if there exists a tower of differential fields, like so, where all of the intermediate things in the tower have the same field of constants, and each extension is either algebraic, logarithmic, or exponential. All right? So that's essentially going to say that we're only adjoining things that are like logs, exponentials, or algebraic elements like polynomials in the original thing.
So if we were to remove the derivations, then adjoining any of these different elements would be the same thing.
Yeah, I think if our derivative is, I feel like if our derivation is 0, then the elementary extension just collapses to an algebraic extension, if I understand things correctly. Yeah. So here's he says if we think of the field as being the rational functions over the complexes, all right, we can think of that as rational functions in the complex variable. Then the elementary extension E is defined to be the collection of all complex functions which lie in some elementary extension C of x. So E is going to be the, it's sort of the differential closure in the elementary sense. It's got all possible elementary differential extensions of C of x in there, right? And so essentially that is the functions which, well, we allow these functions to have domains which are not all of C. Okay. And then E is the field of elementary functions. Yeah. Yeah. If you only wanted to look at extensions of functions on C which have the same domain as C, well, that's very limiting. Like you have to throw out almost every interesting rational function. Your rational functions just become polynomials, right? Not especially exciting. But okay, here's one. Here's an example of a elementary function. E to the cube root, a log of that, the natural log of that is elementary. And he also has an example down here. Just because it's elementary doesn't mean it's something that you know either. Elementary functions can be defined in terms of being the solution set to some relatively unknown differential equation. Like this one, this is the so-called Bring radical. Satisfies this differential equation, which I think means it's a logarithmic extension, or, well, anyway, it's an elementary extension of the rational functions of the complexes. And trigonometric functions, you can also build those from logs and exponentials, so those are also elementary. All right. Moving along here. So lemma, if we have a differential field with extension f of t, if f of t and f have the same constants, all right, and t is transcendental over f, then let's see here. T prime is an element of f, and f of t is positive degree. Then the derivative is in f of t, and the degree is equal to, whoa, well, that's weird. Am I right? Look at that. The degree of f of t is equal to the degree of the derivative. Ah, yeah, that makes sense. And if the leading coefficient is constant, then we get the normal thing back again, all right? And then this 2 here, which to me is too into it for me to get into today. All right, so moving along, that's just kind of a technical lemma. As you can see, here's the theorem. Theorem, let f be a differential field of characteristic 0. Y prime alpha is in the field. Y prime equal to alpha has a solution, y, and an elementary extension of f with the same constants. Then, if that's the case, then there exist constants c1 through cn, n elements u1 through un and v in the field, such that alpha is equal to this stuff right here. All right. So it's something, let's see here. So being able to solve that in this context allows us to solve that, is the Leibniz theorem. Interesting. So what does that mean? Look at, I mean, the proof is wall-to-wall partial fractions. Corollary. Corollary is actually what I'm after. If f of x and g of x are non-zero, all right, complex functions, rational complex functions, basically, and g of x is non-constant, then f of x times e to the integral of g of x dx is elementary, if and only if this f of x is equal to a prime of x plus a of x times g prime of x for some a of x and c of x. What does that elementary mean? That means that this integral is built from basically a finite sequence of sums, differences, products of algebraic, root functions, reciprocal functions, square functions, exponentials, and logarithms, or things you can build from that, like sines and cosines. In other words, it's an elementary function. In the language of Calculus 2, well, we're not quite there yet, right? So that proof just basically uses, it's the corollary, sometimes you see corollaries which the proof is like a sentence, right? But it really is just using Leibniz theorem. It's kind of complicated to use. Leibniz theorem is not the easiest thing to use here. You saw the statement of it. And so this gives us a proof, for example, that e to the x squared is not elementary, because you can sort through the conditions for the corollary and they're not met for this choice of f of x and g of x. And similarly, you can prove that e to the x over x is not elementary. And you can prove, the details are right here. I'll put this handout in course content for you guys, that 1 over the log of x is not elementary. And these are all relatively simple to prove, consequences of that corollary to Leibniz theorem here. And you see that the proof, while technical, can be fit in a couple pages, right? Now, this is just sort of an incomplete, it's part of a larger story, right? So the full algorithm to decide whether or not a function can be integrated in terms of elementary function is given by, I guess this is what, Riche's algorithm, given in the late 60s, and Bill recommends that you read this source here for that. I will post this PDF in all of its glory. I will even give you the tech for it if you want, because Bill gave it to me. So there's the Bill's sources for this. Kaplansky is a somewhat classic discussion of this stuff. More recent books, of course, are the top one. And Rosenlich. He has a really nice little real analysis book, by the way. Okay, so that's differential algebra in a nutshell. So what's differential Galois theory? So differential Galois theory seeks to do for differential equations what Galois theory seeks to do for polynomial equations, in some sense. So start with an integral domain with 1. We get a derivative. You can look at, the polynomial. Well, see this curly bracket? It's R adjoin y and all of its derivatives, right? So it's like the ring and all of its derivatives. And the usual notation for, iterated derivatives. Y is said to be a differential indeterminate. R with bracket y is the differential field called differential rational functions in y. That's the field of fractions of this thing, I think. We can talk about a differential field extension. So let's see if we write that. It's a differential subalgebra V generated by K. and these guys. Likewise, that is the differential subfield generated by K in those. You can look at the Wronskian of a bunch of differential indeterminates, y1 through yn. If you study differential equation, this Wronskian will be familiar to you. And here's one of the central definitions that looms large in this discussion. Picard, how do you say that? Some French person here. Vesio? Okay. That's your fault now, Marissa. All right, so let the record show that was not my pronunciation, but okay, I'll stop. The differential field extension, let E be differential field extension of differential field K. We say that E over K is a Picard-Vesiot. I'm just mispronouncing it a different way. Extension if E has no new constants. In other words, there exists some differential, some L of Y, such that L of Y is basically what? An nth ordered differential equation in Y. So the differential extension has to do with a corresponding differential equation. Just like our algebraic extensions have to do with corresponding algebraic equation. Yeah? And, you know, you can study this. There's the, almost everything you've seen as an analog over here. You can talk about the differential Galois group. It's something like differential field automorphism that fixes the differential subfield K that things are being extended over. Sound familiar? A little bit, right? The K-fixing differential field automorphisms. And so this leads to the discussion of linear algebraic groups. Here's some examples of these things. And this is the fundamental theorem of differential Galois theory. If we have a Picard extension, then G equal to, sorry, Mr. V, the Galois E over K, assume that C is the field of constants, E and K is algebraically closed, then that's the fixed, I guess that's the fixed, E upper H is the fixed subfield, differential subfield of H, I would guess. And that is the inclusion reversing bijection, and its inverse, then from the collection of subgroups of G to the set of intermediate differential fields C. Moreover, H is a closed normal subgroup of that is a Picard V extension, and the quotient is isomorphic to that. Also, if it is Picard V, then the Galois group is a closed normal subgroup of G. This sounds very, very familiar. This is everything we said for the fundamental theorem with what? Differentials basically slapped onto it and the appropriate modification of algebraic extension. And you can talk about integrals, exponential integrals. And finally, L of y equals to 0 solvable by a finite number of integrations if there exists some Liouville extension with differential subfield of L of y equals 0 solvable if its solutions can be obtained after a finite number of integrations, exponentiations, and algebraic operations. So the notion of solvable has some analog here. And eventually, there's the punchline here, I'll just for today. It gets more interesting. Algebraically closed, derivative of x being 1, elementary extension, then a Picard V extension with E contained in there, then the connected component of the identity of that's abelian. Well, that's kind of like all of a sudden we've got some topology appearing. And, oh, come on, where is it? There was a punchline here. I made this a test question last year. Maybe that was it. Liouville extensions have virtually solvable differential Galois groups. L of y equal to 0 is solvable if and only if its differential Galois group is virtually solvable. So it's not quite the same notion as solvable. It's virtually solvable, which is a slight twist on the solvable definition you already know. So anyway, I'll shut up. I know I'm 2 minutes over time, but next time I will start into modules. So, all right. Thanks, guys.